We have already seen KNN classifier. Next, we came into decision tree classifier. Third, what we are going to do is the Bayesian classifier. Right? We have already seen the Bayesian theorem, the Bayesian conditional probability, everything. Now, before going to Bayesian classifier, we need to clearly understand the differences between those nearest neighbors as well as decision trees or Bayesian. You guys are going to attend some MCQs or some like intuitive questions where you will not have that apply level. You need to analyze and then answer, right? So I'll just answer some questions. If you know the answer, you answer very quickly, right? So if I say k nearest neighbors, what immediately you will say in a single word for k nearest neighbors? Like if I give choices like linearly separable data, overlapping data, single classed data, none of the above. If I ask say something, what you will do? K nearest neighbors algorithm. Whether you require any
Overlapping data.
overlapping data, great. Can you explain why? Why the linearly separable cannot be used? Why overlapping only is required?
In other classification algorithms, we will draw any graph or like that. But in
Groups.
overlapping points, we cannot separate them. In neighbor, KNN, we can classify them using distance.
Yes, great. So if I have a linear separator like a line or a plane in case of logistic regression or SVM, I can directly do it with more accuracy. If they are not linearly separable, surely I cannot use them. So if I ask the next question like, if the data is highly overlapping, then which algorithm you will use? I gave you k nearest neighbors, I gave you decision tree, I gave logistic regression, and I gave SVM also. Of these, what are the possible answers? There is no one possible answer. There are more than one. So you select
K,
if the data
K nearest, K and overlapping means.
KNN and
SVM, sir.
no SVM. How can I do SVM with overlapping?
Also Grahan.
I don't mean a kernel SVM. Without kernel, I'm speaking.
Kernel density estimators, huh?
So we have something called as decision trees, which will treat the overlapping data as some outlier something, right? So decision trees can also be used for overlapping data. If they are not linearly separable, also I can use decision trees. Now that is the concept what we are going to take. Now in decision trees, we have two things, totally three things we discussed in the last class. We have entropy, information gain, and Gini. Both entropy and Gini will say how good the split or the decision is going to be there with respect to the
Calculate the impurity
impurities.
of the data set.
Yes, yes, great. So now we have already discussed in the AML class some time that Bayesian is actually the predecessor for decision trees itself. So all machine learning algorithms are actually done in some mathematical way by the great scientist Bayes, right? So they Bayes, Bayes, and their students and anybody have contributed more to statistics as well as machine learning. This decision tree, we have hope you remember this particular data set, the most widely used data set for decision tree learning. Now we need to understand what is the relationship between decision trees and Bayesian classifier and how we can do a particular analysis that to a classification analysis for this particular data set, which we have already done in decision trees. Now, as you rightly pointed out, we have overlapping data in decision trees also. If decision tree is supporting overlapping data, surely Bayes also will support overlapping data. It doesn't require linearly separable data. It can support overlapping data also, right? Now, hope you know, remember this, Bayes classifier is based on a conditional probability. We remember this formula called conditional probability? P of
Last year, Paglaru
A,
alarm.
yes, great.
First year.
P of A given B will be equal to P of
P
B
of
given
A,
A
B given by P of B, A now.
into P of A.
P of A.
I'll take this fraction. Or let me do it direct. Divided by P of B.
B.
No, it is not changing. To have better view, we need this particular notation. This
Enna sola.
you can hear my mic is you are doing some noise. You have A given B, sorry, P of B given A into P of A divided by P of B. That is, this is actually in earlier days, in those days itself, in 16th or 15th century itself, they have said what is training and testing. That is, if we want to find the probability of an output variable, say A, with respect to some set of input variables B, then what we have to do, we need to find there's a relationship between B and A. We know that A is actually the output variable, and if I say that probability of B given A, then that given A is actually called as the training set. Now in machine learning, we call that particular A as training and this particular A as test. So that time itself, they have something like training and the probability of the training data to be available, then to the probability of B. So with respect to B, they are getting the probability of A, that is the conditional probability. Now using this, we have a very good estimator for classification in the name of naive-Bayes classifier. So this naive-Bayes classifier is very much efficient in classifying the given set of inputs, though they are not linearly separable. That is the most important point. Even though an efficient classification technique to act on overlapping data, or it doesn't, I can say like it does not require linearly separable data. I'll increase the font size for betterment. So it does not require a linearly separable data. So the same thing I have said in our decision tree learning also. In decision tree learning also, we have the same thing. And now how the snake Bayes is going to do? In decision trees, we have something called as information gain. And based on what is the gain value, I'll say or take any particular decision. Whether the decision, how good the decision is recognized by either entropy or gaining. Now here in the naive Bayes, same thing I'm going to use, but instead of using those metrics like entropy, gain or something, I'm going to use something like a probability that is called as a conditional probability. With what probability I can say the particular children with this particular condition can go and play tennis. With what probability I can say that with the same condition I should say he should not go and play tennis. So that's what I have to identify and say. So this is actually my task in Bayesian learning. So what I will actually do is I'll take the data set into consideration and I'll use those formulas, right? Now I'll go into the thing. Now if I want to do such the Bayesian classification, what I actually have is I have a set of data here. I look into the attributes. So what are the attributes I have here? I have outlook, I have temperature, I have humidity, wind, and play tennis is going to be my input variable. So initially what I will actually take is I'll take the individual values of each probability. Say for example, we'll go in a step-by-step manner. I come here, I show this table also, this is also most needed, right? Now, what is the probability of playing tennis? Right, let me take a total probability, right? I'm saying that what will be the probability of play tennis equal to S? What will be the probability of play tennis equal to S? 1, 2, 3, 4, 5, 6, 7, 8, 9. And what is the total sample? Total sample is 14 and number of S is 9. So what will be the probability to say that play tennis is equal to S?
9 by 14.
9 by 14.
Yes, I can say it is 9 by 14. So if I take the calculator and put, I'll get something like 0.64 approximately, right? In a 2-degree precision. And similarly, what will be the probability of saying it no? Since it is binary, you can take 1 minus, or
5
you
by
can calculate the thing and say 5 by 14 is. And this will be 1 minus 0.64, or if I do 5 by 14 also, I'll get 0.36. So this is actually the way in which actually we proceed and see how the total probability actually lies. With a given data set, 64% of time we are allowing that particular child to go and play tennis, and 36% of time we don't allow the child to go and play tennis. This is the overall probability of the entire set. Now, this overall probability is the normal statistic. Now, what I will introduce is, I will introduce the conditional probability for this. What is that conditional probability? The overall probability says 0.64 to play tennis. What is the probability to play tennis given outlook is equal to sunny, temperature is equal to hot, humidity say high, and wind is strong? So I give some conditions, and based on that conditions, what is the probability? I'll ask that particular question. So that is the case over here. So whenever you are given a data set, you first calculate all possible probabilities that is required for your attributes. Now I'll take the first attribute as outlook. So if I take the attribute of totally of 1, 2, 3, 4, 5 sunny is there. So 3 goes here. So 3 sunny is going here. Overcast, what will be the value for overcast? Yes, 1, 2,
4.
3,
4
4.
by 9, sir.
4. 4 by 9, right. So this side, I think everything is 4 here. So I think, shall I put 0 here? Am I right? Yes, I think no overcast is giving me no. Right. Similarly, rain 1,
3 by 9,
2.
sir.
Okay, minus 3 by 9. Hope it is verified. Next,
1 by 5.
1 by 5. Totally 4 rains are there, it seems, right? I think we are missing one value. 1 to 5 rains are there. So no, 2 no's are there, right? Am I making it clear, or am I going anything wrong? Is it fine?
Correct, sir.
Yes. So this is with respect to outlook. This is conditional probability degree 1. What is that conditional probability degree 1 in the sense? Probability to play tennis given sunny is equal to S. When sunny says yes, when outlook is equal to sunny, what is the probability we have obtained here? So I just write here. Yes, this is with respect to outlook is equal to sunny. I mark this, right? Next, what will be my next one? And outlook is done. Yes. Temperature. For temperature, I'll take how many temperature values there? Hot, cool, and mild is there. I'll take a similar table. Hot, cool, mild, yes, no. So I'll take this table. We have the temperature ready here. Temperature. And I can have 10 is as yes. Output variable is there. Yes and no. And I can have hot, mild, and cool. I can have 3 values over here. Now, with respect to this, how can I actually group it? Let me actually reduce the size of this table. Keep it somewhat here so that we can see the table very clear. Yes. Total is actually, we are already fixed with the total number of yes and no's. We know how many yes is there, how many no is there. So the denominator is actually fixed. So we can have the denominator fixed divided by 9. This is divided by 9. This is divided by 9. And then here it is divided by 5. This is divided by 5. This is divided by 5. So I have this here. For how many heart I will be having the values to be set as yes. I'll have heart is equal to S for 1. Next, heart is equal to S 2 times. 2 by 9. Next, 2 by 9 is over here. Then how many no will be there? Heart no. Heart
2 by
no.
4, sir.
2 by 4 in the sense, actually denominator total is 5 for no. So out of 5 no's, how many heart is actually no? 1, 2. I could get only 2. Is it 2? Is it 2?
2 by 5, sir.
Yes. Right. Similarly, mild. Mild is equal to S. 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 So 4 by 9 here. and mild equal no, mild equal no. I think 2. Yes, 2 by 5. Right? I am making it clear. 4 and 2. And finally, cool. Cool is equal to S. Cool 2. Cool is equal to 3. Yes, 3 by 9. And here I can find only 1. 1 by 5. Right? So this is with respect to temperature. Great. So we have the temperature also ready. So this is the next given temperature is hot. What is the probability to play tennis given temperature is equal to cool? That is the thing we have brought over here. Now we'll go with the similar thing. Now finally, still two more is there. The next one will be this particular humidity column. I'll take that. Right. So for humidity, I have high and normal. Only two is there. So we'll then take that. Insert table. Humidity high, normal, S, no. So I'll get this. Humidity high. Sorry. This is over S and this is over no. High, normal. So that is the size of the table. Yes. Let us go up and see why we put divided by 9. Because the total number of S is 9, total number of no is 5. So we put 9 and 5 directly. I go here. How many high says yes? 1, 2, 3. 3 high says yes. High no, high no, high no, high no. So 3 and 4 over here, I hope. I am making it, am I correct? It is 3 and 4. I'll show the table. If any of others also can verify and let me know if I was going anything wrong. Similarly, normal is yes, normal S, normal S, normal S, normal S. I think except one normal, all the other normal are actually yes. So I can find a 6 normal as yes. 6 by 9 and this is finally 1 by 5, right? So this is actually with respect to humidity. I got this with respect to humidity. Power condition probability degree 1. Final thing is wind. Wind can be either weak or stronger. So I can say that weak and stronger thing. Again, I'll construct set. We'll have wind weak or strong, yes or no. So I'll construct that wind weak, strong. I'll put either yes and no. So we have this ready. It is not moving away. Okay, it's not going above. Let us have this weak yes over here. So wind. How many wind says how many weak yes is there? 1, 2, 3, 4, 5, 6. Is it 6 years? Kindly verify and say whether it is 6 years for week. And how many strong is there? Is it 6? Students? Say how many S is there?
For week 6, sir.
Okay, 6 for week. Okay. 6 divided by 9 I have. And how many no will be there for week?
3 by
I'll
9.
show the table. The table is there here. How many weeks says no?
2 by 5, sir.
Oh, sir.
2 by 5. Okay. So I'll put 2 by 5. Similarly, now you see strong also. So we will put together there. Strong no. Strong no.
3 by 5, sir.
I'll come here. This is actually 2 divided by 5. And with respect to strong, this is actually 3 by 5 as you said. And what is this?
3 by 9.
Okay, 3 by 9. Hope it is verified. Now we have all the conditional probabilities. Degree 1 means that only one condition is given. So what is the probability to play tennis given it is weak? Those things we actually calculated. Right? When I ask you questions also, I may ask some easy questions like if I give a data set, I'll be asking you that degree 1 probability only I'll ask. Degree 1 probability, you can easily check this and then you can immediately answer within 1 minute or 1.5 minutes. So that thing you have to do, right? Now going into the actual question, what is the probability to play tennis, right? To play tennis if my outlook is going to be sunny. So we have the individual probability for sunny, humidity, wind, and temperature, everything. So what is the probability to play tennis with following conditions? So the conditions are we have outlook equals sunny, temperature equal cool, and humidity equal high, and we can have wind equal strong. We have this, right? So with respect to this condition, I have to solve. Now, if I see individually, if outlook is equal to sunny, what is the probability? I know. If temperature is equal to cool alone, what is the probability? I know. But if I need a combined probability, then what I have to do is I need to increase the degree. This is actually the conditional probability with 4 conditions. So I can say it is a conditional probability with degree 4. Now we can see a very simple formula of Bayes is Bayes classifier. We take an equation V NB. NB corresponds to Bayes. It can be calculated as an argument max. It is going to the argument max is going to be what are the maximum values a particular attribute can have. The maximum attribute a particular value can have is nothing but outlook can have 3 values like sunny, overcast, rainy. Temperature can be hot, cool, medium, or humidity can be high, strong, medium, like that. So how many arguments it is actually having in maximum, and it will be the output variable. If I need to do the classification for output, what are the classification I have here for the output? I have only 2 values. One is either S or another is no. So now I go for the output variable argument maxing. So output variable can be either need a subscript. V can be take some symbols and then put inside. V belongs to either S or no. So that is the value what we actually have here. V belongs to either S or no. Next, probability of V underscore probability of I can have this as Vj. I can just have it as this particular variable. This is actually can be considered as Vj. This word latex is actually not supporting much. Please wait for a while. It is actually loading. So the formula is very simple. You need to take the probability with respect to all the values. I have outlook sunny. Outlook is equal to sunny. Temperature is equal to particular thing. Humidity is equal to high, and wind is equal to strong. So I take the individual probabilities. I multiply them together. That is actually the total probability. Actually, I just multiply them together and I get the result. So that is what I'm going to do over here, right? So this word is actually not responding here. Word file, and then I go to that. Once it is actually completed loading, I'll go to that particular file. So let me do it in this empty file. Let's write a formula for naive Bayes. Right, this new word file is visible, right?
Yes, sir.
Yes. So the naive Bayes classifier formula, let me write over here. Naive Bayes classifier as, I'll be having B underscore, I'll be having the formula as BNB. This BNB corresponds to the classification variable. So this, so we call it as a naive Bayes classifier as BNB. That will be called the argument max of the B value. What I actually take over here will be in either what will be the output variable. Either it should be V should be classified as either yes, or V should be classified as no. And that I have to take. So V belongs to either yes or no. I will be taking the what will be the total probability. The total probability is nothing but what are the conditions that is actually being given, and with respect to those conditions, what will be the probability I need to take. So what will be the total probability of being either yes or no? I'll take that first. What will be the total probability? Into, I'll be having a multiplication scenario here. Into, I'll take that particular symbol. Yes, this is. Can take this. So it is pi represents the product. We know summation represents sum and pi represents product. So the product is going to be either probability of the particular attribute, say AI, right, into given the probability V. Given what the probability you actually require, that probability say V. So this is actually the case in naive Bayes algorithm. So this is what we have to actually I want to do with respect to the thing. Now we actually have this attribute everything set. My first attribute what is set is outlook will be sunny, and what will be the sunny value with respect to yes. If I asked you to calculate with respect to yes, you do that. Then you calculate with respect to no, you do that. Here we have something like argument max. Means that for either for yes, what is the probability? For no, what is the probability? You take separately and say which is maximum. If the probability for S for the given attribute conditions is high, then you classify that particular condition as yes. Otherwise, you classify that particular condition as no. So this is actually the case over here. Now, has anyone taken the screenshot on what is the thing? If I have that, right? So we take that particular thing, we have V and B as, first I'll go with S, V and B of S. So I take V underscore N, V and B, now I'll take with respect to S alone. So what will be the classification if I take V and B is equal to S? My probability will be probability of S, the total probability of S, into, I say outlook is going to be sunny. So how many sunny is actually contributing for S? Next, probability of, I have another condition as temperature is equal to cool. So for outlook is equal to sunny, what is the thing? For temperature is equal to cool, what is the thing? Everything you can take. This is actually outlook is equal to sunny with respect to S. Next, temperature is equal to cool with respect to S. Next, I have humidity is equal to high. Humidity is equal to high with respect to S. And finally, everything you can write it as a separate probability. So this is actually probability into probability of humidity is equal to high. How many humidity is equal to high is contributing S into probability of finally is wind. Wind is equal to strong given S. So this probability I'll be taking and then I'll do a normal multiplication. So we have already calculated what is the total probability of being S, what is the sunny given as, and what is cool given as, high given as, and strong given as. We have the calculated that individual values already. So we can use those values and get the result itself. We don't want to do it again. We already found out the degree 1 conditional probability. I'll take that degree 1 conditional probability and I'll use that for evaluation, right? So what I will do is, I'll try to find whether the earlier word file is now ready, whether it is responding now. Anyway, I didn't save that. Yes, it is ready. I'll take this and I'll put it there. Yes, can you see this word file, which actually we are already working on?
Yes, sir.
Yes. So now if we go up and see what is the formula we already have, right? So we have the formula here, all the values of conditional degree 1 probability is available. Now we need what will be the probability of S. I just go above and check what is the probability of S over here. What is the probability of S? That is the total sample probability. If I want to calculate probability of S, what is that?
9/14.
That is, I can take it as 9/14 or 0.64 I can take. Or as she says, we can take it as 9/14 itself. So what will be this will be equal to 9/14 and outlook is equal to sunny given S. So I go here, this is my outlook table. Outlook should be sunny and play tennis is yes. So what is the probability?
2/9.
Yes, I take that 2/9 and I put it here into 2 divided by 9 and I have temperature cool S. So I go to the temperature. So for temperature cool to be yes, I have 3/9. I put it that here. And wind is equal to strong given S. So I have the wind here. For strong, it will be 3/9. Humidity we miss, right? Humidity to be high and S is 3/9 again. So this is 3/9 into 3/9. Yes. So we have that everything ready. We take everything from the upper values and then we substitute here and see what is the total probability to allow whether the child to go and play tennis or not. Now I take the calculator and do this. It is 9/14 into 2/9 into 3/9 into again 3 divided by 9 into 3 divided by 9. So what is the value I actually get is 0.005. Is that value you are also getting? I can put more value, 0.00529 or something it is coming. So I put 0.0052 as the total value. Now this is my first argument. I need to take the maximum of either S or no. Probability of S for these particular condition is going to be 0.0052. And similarly, I can calculate what will be the probability of no. I'll finish it quickly. So I take this, I find what is the probability of no. Instead of this particular S, I use no. So everything will now become no. So I need to take the probability of no with respect to everything. So sunny will become no. Temperature becomes no. High becomes no. These have attributes. How many times they are actually supporting the no values. I'll take that and I'll do that particular calculation. So quickly I'll do that. Probability of no is nothing but 5 by 14. So quickly can you say me so that I can finish it quickly? 5 by 14. And Sunny to become no is 3 by 5 and 1 by 5. And over here it is, you also remember so that if I forgot, you just give it to me. 3 by 5 and 1 by 5. So I take it and put here. 3 divided by 5 into 1 divided by 5. And what is next for humidity to know?
4 by 5.
4 by 5. Wind? Wind to become strong and no. Yeah, what is wind? Wind should be strong, no. 3 by 5. So we'll quickly find our total value. That is 3 divided by 5. So my result will be, this is 5 divided by 14. I'll take the calculator again. So this is 5 divided by 14 into 5 divided by 14 into 3 divided by 5 into 1 divided by 5 into 4 divided by 5 into 3 divided by 5. So I get like 0.2057 and it goes on. So I put here 0.2057. Right? Now you take the argmax of this S and no. For this condition, which is actually maximum, either 0.0052 is maximum or 0.2057 is maximum.
0.2057.
Yes. So I can take like V underscore N, V N B is equal to argmax of either S or no. For S, it is actually 0.0052 and for no, it is 0.2057. So I'll take it is going to be 0.2057 classified as no. Hence, if in the given condition, if outlook is equal to sunny, temperature is equal to cool, humidity is equal to high, and wind is equal to strong, then I write like Platonus is equal to no. So this is actually the final answer. Then Platonus is equal to 0. And if then condition like decision trees itself. Right? I am making it clear with respect to the Bayesian. We have already seen it, just a recap. Right?